Okay, so here we are in the last section of the book that we need to cover, actually. It's 10.8. The topic is vectors. This is a pretty long section. There's a lot of material that we cover, but it's very, very important, the topic of vectors. I can tell you just from my experience in teaching these courses that the tricky thing with vectors is that we teach it here in trigonometry, and then you don't really see it again until Calculus 3. Calculus 3 deals with multivariable and vector calculus, and there's a good stretch of time between now and when you would be taking Calculus 3. And I'm currently teaching Calculus 3, and I can tell you that one of the difficult things for me at the beginning of the semester was students not remembering these important results about vectors. So it's a very important topic, but you're not going to see it in Calculus 1 or even Calculus 2. So please don't forget this stuff. Let's go ahead and start talking about what a vector is. There's a lot of terminology to cover. Basically, what a vector is a mathematical object that possesses two measurable quantities, which we call magnitude and direction. Typically, a vector is represented using arrow notation. So you're seeing vectors in these examples here. You'll notice there's a blue and a red arrow. We're going to talk about this one in more depth once we get a little ways further. The magnitude of a vector is the length of this arrow. That's what the length represents. The direction of the vector is going to be the angle that it creates with the positive x-axis. When we put vectors in this notation, this arrow notation, the end point of the arrow that does not have the arrowhead, we call that the initial point of the vector. And the point that has the arrowhead on it, we call that the terminal point. So in this example, my initial point is x1, y1. My terminal point is x2, y2. Now, any two vectors, if we're representing them as arrows in the plane like this, are considered to be equal if they have the same magnitude and direction, even if their initial and terminal points are showing up in different places. That is, they should be pointing the same direction and they should have the same length if they're going to be called equal. So in this example here, this blue vector and this red vector, we can confirm just by measuring that they both have the same magnitude and direction. We would say that this blue vector and this red vector are equal to each other, even though they appear in different positions on the plane. In fact, I can make several copies of this vector, this red vector, and place them all over the place in the plane, and even though they all have different positions, we would consider all of them equal. So the position of a vector in the plane does not change the vector as far as we're concerned. There's one special vector worth singling out. We call it the zero vector. The zero vector is the vector that has a magnitude of 0, meaning a length of 0. So another way of thinking of that is that the vector's initial and terminal point are the same point. If we want to put a vector in the plane, we represent it by a point, because we can't put an arrow that would give it length, which it's not supposed to have. Because there is no arrow notation that we could use in the case of the zero vector, we don't know what direction it's pointing, so we just say that it has no direction at all and a magnitude of 0. All other vectors will have a positive magnitude in some direction. Okay. As far as the notation that we use for vectors, if the vector has an initial point at P and a terminal point at Q, we can notate the vector this way, PQ, with an arrow over the top. But we tend to only use this type of notation if we need to be able to call attention to the initial and terminal points. Oftentimes we don't need to know what the initial and terminal points of a vector are, and in those cases you'll see more often we're using a bold notation. So I oftentimes use letters like U and V and W, things close to the end of the alphabet, lowercase letters when I'm talking about vectors. If you're using, like something that's been typed out like this page, then you can put that in bold. However, if you're doing this handwritten, it's hard to make a bold letter in pen or pencil. So as an alternative, when we're doing handwriting, we usually put that little arrow notation over the lowercase letter, and that represents that vector. Okay, moving right along. Let's suppose that we're working with a vector, and we know its initial and terminal points. I'm going to say the initial point is P, which has coordinates x1, y1, and the terminal point Q has coordinates x2 and y2. That's like this blue vector right here. You notice I've given those same coordinates to this vector. We refer to the change in the x and y coordinates as you go from the initial point to the terminal point as the components of this vector. So let's look at this more specific example right here. Here's P and here's Q. If you can see that, the coordinates of P are 2, 3. The coordinates of Q are 6, 4. Now, if I wanted to do this in a very, kind of basic way, what I would do is start at my initial point and find how far am I moving horizontally and how far am I moving vertically to get from the initial to the terminal point here. So if you count, you go 1, 2, 3, 4, 5 units or actually, this has been mislabeled. This is straight out of your book. I'm looking at this, and it's saying 6, 4 here, but it actually goes to 7, doesn't it? Let's fix that. This is going to 7, 4. All right, looks like this is correct. That's actually going to change this as well. But if you count horizontally from the initial to the terminal, we go 1, 2, 3, 4, 5. And then from here, we go up 1. So that would mean my horizontal component is 5 and my vertical component is 1. This needs to become a 5 now because of that. So that's very small. To make that notation a little bit bigger, we would write the vector notation or the component form of that vector like this. We use angle brackets instead of parentheses, and these represent the components of that vector. Again, how far horizontally do we go and how far vertically do we go when we move from our initial to our terminal points. Now, you don't want to have to rely on counting these out to do this. What you're going to want to do instead is use a formula, and it's very simple because if you're looking for the change in the x direction, that's simply the x coordinate of your terminal point minus the x coordinate of your initial point. That would give you that first component. Similarly, y2 minus y1 would give me my vertical component. So if a vector, if you have a vector PQ like this, initial point P, terminal point Q, and its component form looks like this, A, B, we can find A and B just by taking the difference of the x coordinates and the difference of the y coordinates, always in the order of terminal minus initial. If you do it the wrong order, you're going to get the opposite of what you want. Okay, so that's called putting it in component form. Now, if, like we said before, if you take a vector and keep its magnitude and direction the same, but move it around in different positions in the plane, then we consider that vector to be equal no matter let me say that differently. Any two vectors with the same magnitude and direction are considered equal, even if their positions are different. However, if we take a vector and put its initial point at the origin, we refer to that vector as being in standard position, and we can call that vector a position vector. Now, the benefit of a position vector, and you can verify this just by thinking about it for a second, is that if you have a vector in component form and that vector is in standard position, then the components of your vector are going to be the same as the coordinates of your terminal point. See if you can make sense of that with the diagram. So, a lot of terminology, a lot of, kind of running through some of the basics of vectors. Here's our first example. I want to find the component form of a vector with an initial point of 1, 3 and a terminal point of -3, 5. So the component form is going to come from taking the difference between my x coordinates of these points, always terminal minus initial. So that's -3 minus 1. And then again with my vertical or my my y coordinates, 5 minus 3. Okay, doing the subtraction, I get that the component form of this vector is -4, 2. Now, in addition to that, it says graph the vector with these initial and terminal points as well as in standard position. So basically what it's asking us to do is what these diagrams have done. We graph the vector with the originally stated initial and terminal points, and then we graph that same vector but as a position vector. So starting with the initial and terminal points, let's find those. 1, 3. So 1, 1, 2, 3. Put that here. That's my initial point. And negative 3, 5. So I'm going to need more space here. Negative 3, 1, 2, 3. 1, 2. Let's put 5 up here. Initial terminal. That means the vector looks like this. Okay. Now we want to represent this as a position vector. So the same vector, but moved so that its initial point is at the origin. And like I said before, if you know the component form of the vector, and the vector is in standard position, then this will also give us the coordinates of the terminal point. So my terminal point is going to be negative 4, 2. Negative 4, 2 is right here, so that means I'm looking at this vector. Obviously, this was sketched by hand, so you can't completely trust the scale of things, but you can see that based on my attempt here, that the vectors do appear to have the same magnitude and direction, as they should. They are the same vector, just placed in different positions. Okay? All right, let's focus on the magnitude and direction now. We've talked about component form for vectors. Whoops. If you have a vector that's been given to you in component form, so let's say v is in component form equal to ab, then putting that vector in standard position reveals a connection between the magnitude and direction and the components of that vector. Notice the components of this vector, ab, would correspond to the base and height of this little right triangle right here. The magnitude of the vector could then be thought of as the hypotenuse of that right triangle, and the angle theta here is like one of the base angles of that right triangle. We've seen this diagram numerous times in different forms. So when we talk about polar coordinates, for example, if this is the point x, y, and this is r and theta, we have conversion formulas between rectangular and polar coordinates that we derived from a diagram just like this one. Those formulas are going to be the exact same, just with this new notation. So when we want to talk about the magnitude of the vector v, notice we use something similar to the modulus or absolute value of a complex number. We use absolute value notation. So this represents the magnitude of v, the length of that vector, and based on those formulas that we've already derived, that's equal to the square root of the sum of the squares of my components a and b. It's really just from Pythagorean theorems where that comes from. Similarly, we've seen this one as well. The theta, tangent of theta, is equal to b over a. So I can find my magnitude and my direction straight from the components of my vector. Similarly, just like how we derived those conversion formulas between polar and rectangular, if I'm going the other direction, for example, if I'm given the magnitude and direction of a vector, then I can put v in component form using these formulas. The horizontal component, which again would be the same thing as the x-coordinate of my terminal point if this is in a standard position, is going to be magnitude of v times cosine of theta. Similarly, b would be magnitude of v times sine of theta. So let's do this in both directions. I have a vector in this first example here where I want to find the magnitude and direction. It's going to be helpful to me to actually graph this vector first. So again, remember, if I put this vector in standard position, which is the easiest way to visualize it, notice it doesn't tell me any initial or terminal point, so I can place this vector anywhere I want. My horizontal component is 3, so I go 1, 2, 3. My vertical component is negative 3, so 1, 2, 3. Negative 3, 3. In standard position, this vector is going to look like this. Okay? Now, I want my magnitude and my direction, so I'm using those formulas. Well, the magnitude of this vector, which we use absolute value notation for, is equal to the square root of the sum of the squares of the components, 3 squared plus negative 3 squared. That's 9 plus 9, or 18. Square root of 18 is 3 root 2. That would be the magnitude. That's the length of this vector. Theta, remember I have this. Tangent of theta is equal to b over a. That's negative 3 over 3, or negative 1. Remember, I can solve this by either using my unit circle or an inverse tangent and being careful to pay attention to the quadrant that we're in. If I took an inverse tangent of this, I would get negative pi over 4, which would put me in the fourth quadrant. And it looks like that's where I am. So that's great. I can use the inverse tangent in this case without having to add a pi to it. Theta is equal to negative pi over 4. Okay, so there's my magnitude, there's my direction. Sometimes we may be asked to keep the direction within one revolution of the unit circle. So in other words, I may not want to use negative pi over 4 if the problem is asking me to keep my angle between 0 and 2 pi. So in that case, I'd find a coterminal angle to this. Notice 7 pi over 4 is the same angle in a coterminal sense, but it's between 0 and 2 pi. Okay, so either of those would work. Going the other direction, I want to find the component form of a vector v whose magnitude is 6 and whose direction is 5 pi over 6. Well, using those conversion formulas, my horizontal component is going to be the magnitude of v, which is 6, times the cosine of the angle, or the direction, 5 pi over 6. And similarly, my horizontal component would be 6 sine of 5 pi over 6. Okay, this would be equal to 6 times, so this second quadrant cosine is going to be negative here, and the cosine of 5 pi over 6 would be negative root 3 over 2, and then 6 times sine of 5 pi over 6, sine is positive there, and it's equal to 1/2. This gives me, after some cancellation, negative 3 root 3 3. That would be the component form of that vector. And all I did is I used those conversion formulas, putting them into the components right away. Okay? All right. So we've covered kind of the most basic stuff with vectors. A couple of things I want to point out before we move on. You can see here we're going to do some operations with vectors: addition, subtraction, and a special type of multiplication that we call scalar multiplication. One thing I want to point out, going back here, again, this vector notation we've been representing by arrows in the plane. Vectors can also exist in 3 dimensions. We just don't talk about it in this class. You'll be introduced to that in Calculus 3 if you're going that far with your math education. In those cases, we make similar definitions for all of these things. If you ever take linear algebra, you learn that you can generalize vectors to far, far greater extents than 2 or 3 dimensions. But all of our work here is being done in 2 dimensions. Now, with that said, what exactly are we doing with vectors? I'm talking about them as having magnitude and direction and being represented by arrows, but what connection does that have to anything in the real world? Well, to make some sense out of this, the vectors are really used for a lot of different things, but probably one of the easiest things to motivate is the application to forces in physics. And here's an example. Imagine that the page here is like an ice skating rink, and we're looking with a bird's eye view, looking down on it. On this ice skating rink is this box with some weight to it, and there's a couple of forces acting on this box. Imagine that at some point on the top of the box here, there's a rope that's attached, and let's suppose like a really strong Olympian, is pulling on this rope that direction. All right. Then this arrow is going to represent the force that the strongman is exerting on this box. Now notice it has a magnitude, and the magnitude is just the quantity of that force. How hard is he pulling on this box? The direction that it's pointing is the direction that he's pulling. So that gives direction and magnitude meaning in the context of this vector. Now suppose my 6-year-old son attaches a rope to the same spot, but pulls in a different direction. Maybe he's pulling up. Well, my 6-year-old is strong, but he's not as strong as this guy. So when he pulls in this different direction, he's going to be pulling with a lot less force than this strong man, right? So this arrow is going to represent the force exerted on this object by my 6-year-old. And by pulling it this direction, he's only pulling with a small amount of force compared to this guy over here. So the question now is, what direction will this box move? And if you think about it, it doesn't take, a whole lot of thought to come to this conclusion. It seems like it's going to be moving this direction somewhere, right? We don't expect it to move this direction because neither of the forces are going this direction at all. But we don't expect it to be going at a 45-degree angle this direction either, because the horizontal pull is much, much greater than the vertical pull. It should be pulled much more in a horizontal direction than a vertical one. But it's also not going to move completely horizontally because there is some force acting upwards on this thing. So in order to interpret what the combined result of these two forces is, we use what's called a resultant vector. If I were to take the strongman's arrow, the vector representing his force, and sort of do a copy and paste, so basically copy it so its initial point coincides with the terminal point of my son's force here. And then if I do the same thing with the smaller force, copy and paste it over here, so that the initial point of the smaller force coincides with the terminal point of the greater force, I've created this little box. If I then join the initial point that they have in common to the terminal point that these two vectors that I just copied have in common, this diagonal is what I would call the resultant vector. And what it represents is the combined forces on this object. It's going to predict the direction that this box will move and with what combined force. Notice these forces aren't really working completely in opposition to each other. Otherwise, they would be pulling in opposite directions. So that is going to give some meaning to the concept of addition when it comes to vectors. And I think I'm looking at the time on this video. I'm going to save that explanation for the next video.